There are a few things I want to clear up before we move forward. And the first is all of these fatigue factor of safety calculations we throw on top in the tensile mean stress sector. So we're talking about mean stresses here that are all tensile, and we have stress amplitudes over here. We draw these various lines by connecting the fully corrected endurance limit to either the yield strength or the ultimate along the mean stress axis. The Goodman equation is the one that drew a straight line between SE and SUT. Now recall, SE is calculated using all of the Marin factors after we first estimate SE prime. So now all of these factors of safety are based upon which of these lines in here we're going to be using to calculate that factor of safety. The Langer yield line simply connects the yield strength on the amplitude axis to the yield strength on the mean stress axis. It is this dashed line right here. We use that to determine whether or not we're going to have yield. All the other lines are criteria, the Goodman, the ASME elliptic, the Gerber line, are fatigue-related criteria that account for the mean stresses. The Soderberg line simply connects SE on the amplitude axis to SY on the mean stress axis and is the most conservative failure line. Remember, everything that falls below whatever line you are choosing as your failure criterion line is going to be safe combinations of stress amplitude and mean stress. So our stress amplitude will be pulled off here. Our mean stress will be pulled off here. If we are below the failure line, we are safe for infinite life. The other thing that we are doing with this diagram is we're using it to find our factors of safety. So we're trying to find fatigue factors of safety by using these diagrams. Well, let's imagine that we're looking at the modified Goodman line right here, and we identify a loading line, and the loading line is going to have a slope which is equal to the rise over the run. So the loading line has a slope of stress amplitude divided by mean stress. The intersection with the Goodman line identifies this particular mean stress amplitude combination. But we may well have a stress amplitude mean stress combination that sits right here. So we have an SA and an SM, that is our mean and amplitude stresses, that sit right here. And how do we calculate the fatigue factor of safety? And what we do is, for this particular load line with the slope given by SA over SM, and it could be our green one, remember, SA over SM, that's perfectly legit. What we do is we measure the length of the line out to where it intersects our particular fatigue failure criterion, and we measure the length of the line for our particular load application. And so this length, I'll call that capital L, this length is L. The fatigue factor of safety is simply capital L divided by little l, and it's just the relative lengths of the lines relating to your particular combination of stress amplitude and mean stress, and for that given load line, where it intersects your given fatigue criterion. Remember, when you're out here on the boundary, your fatigue factor of safety is equal to 1. If you are below that, your fatigue factor of safety is going up. So it's simply a ratio of lengths along the load line, where the one length is all the way out to the fatigue criterion of interest, and the denominator is simply the length of line out to your particular combination of SA over SM. There is another point that I want to raise here, and that is we are using mean stress corrections for mean stresses greater than 0. We use a mean stress correction. We know that as you increase the tensile mean stress, then the allowable fatigue amplitude must drop. In fact, we said that your stress amplitude divided by your endurance limit plus your mean stress divided by your ultimate tensile strength is equal to 1 over the fatigue factor of safety. That is the Goodman criterion. Well, if your mean stress is less than 0, then you are simply going to be ignoring this this term. If sigma m less than 0, ignore sigma m. Just let it be equal to 0. Now, you might ask yourself, what if I have a stress situation where my mean stress is less than 0 and I'm fluctuating about that mean stress? Will I have fatigue? Well, you still have a stress amplitude, so in fact, you will still have fatigue. You simply do not include the mean stress in the calculation of the factor of safety for infinite life. Now, if we have finite life, we have a combination of stress amplitude and mean stress that is above the fatigue criterion. It means that we have moved out here above our fatigue line. So we have a combination out here, and that's going to give us finite life. So how do we handle a finite life problem? Well, what we do is we remember that when we collapsed all the finite life curves onto a single diagram, we got a relationship that looked like this. Well, we can rearrange this and solve for sigma AR, which is going to be my stress amplitude divided by 1 minus my mean stress divided by my ultimate. What we know is that sigma AR is governed by Baskin's law. So sigma AR is going to be some A times number of cycles to failure raised to a power B, where B is negative. We simply replace sigma AR with that, and we find that sigma A is going to be equal to A NF to the B, that was our sigma AR, times 1 minus sigma M over the ultimate tensile strength. So for any combination of stress amplitude and mean stress, we could then solve for the number of cycles to failure if we know the fitting parameters A and B. So you know we have to find the fitting parameters A and B. If we look at this equation right here, that our stress amplitude is A NF to the B times 1 minus the mean over the ultimate. We just have to find the fitting parameters A and B. How do we find those fitting parameters? We go back to the SN diagram, where this is our number of cycles to failure and this is our stress amplitude. And you know that we have a low cycle fatigue regime that's at 10 to the third cycles to failure, and out at 10 to the sixth, infinite life. This is the high cycle fatigue regime. That's where we can use Baskin's law, ANF to the B. We have to find the parameters in there so that we can then calculate the number of cycles to failure. We have previously said that this point at the end is just some fraction of the ultimate, that this point at 10 to the third cycles is a fraction of the ultimate tensile strength. This is the ultimate tensile strength here. This is supposed to be stress amplitude. So if we know this end, we know that at 10 to the third cycles to failure, the stress amplitude is FSUT. So we come up here and we say FSUT is equal to A1 times 10 to the third raised to the B power. What else we know is that down here at 10 to the sixth cycles, that our endurance limit, SE, is the fully corrected endurance strength. So at 10 to the sixth cycles, we know that the stress amplitude is SE, and that's going to be A1 times 10 to the sixth to the power B. These two equations allow us to solve for A and B. But we can't do that until we know what F is. So I just mentioned that we have to find the fitting parameters for Baskin's law. I have a tendency to use capital A instead of lowercase a, but the book uses a lowercase a. Here are the two equations that you need. We need the fully corrected endurance strength. We need the ultimate tensile strength, both here and there, and we need this fraction F. So the only way we can find that fraction F, it seems, is to read it off of a curve. But there is a way that these curves are generated using the following formulas in equations 610, 611, and 612. You may recall that we used the Coffinmanson law to relate strain amplitude to the number of reversals to failure, where we said that that strain amplitude was going to be equal to sigma F prime over E times 2NF to the B plus EF prime times 2NF to the C, where EF prime is the true strain at failure and sigma F prime is the true stress at failure. So in the HCF regime, the plastic strain is going to be assumed small, so we're going to ignore this term. So then we multiply through by E and we get that E times the strain amplitude is equal to sigma f prime times 2nf to the b. Remember, this is all simple approximations. This over here becomes a reversed strain amplitude. So that's equal to sigma f prime twice nf to the b. At 10 to the third cycles, we have already said that the stress amplitude would be some fraction of the ultimate tensile strength. And so F times the ultimate tensile strength would be sigma F prime times twice nf to the b. So our fraction F would be given by sigma F prime over the ultimate tensile strength times 2 times 10 to the third cycles raised to the power b. So there's our fraction F. Now, if only we could get B and sigma F prime, we can always find the ultimate tensile strength, we would be able to write an equation for F. So we're going to be looking for estimating sigma F prime in a moment. But the next thing we're going to do is we're going to look at 10 to the 6 cycles, which we're going to call our endurance limit. We know that our endurance limit is going to be equal to sigma F prime times twice NE to the power B. Well, what can we do with that? This SC, we're going to do our original estimate where it's equal to half the ultimate tensile strength. So we're just going to call that SE prime. And that then is going to allow us to solve for B. So if we do that, we're going to get equation 612 right here. It says that B is equal to minus the log base 10 of sigma F prime divided by the estimate of the endurance strength, SE prime, all of that divided by the logarithm of twice the endurance number of cycles to failure. Once we have that, we go back up to this equation and we solve for F. So we can find B if we can estimate sigma F prime. The SAE estimates of sigma F prime in English and metric units are given by equation 611. So use 611 to estimate the true strength at fracture. Then use 612 to find the exponent B, then use 610 to find F. And that is exactly what I did in my spreadsheets.